Hey guys, welcome back to my AP Chemistry playlist. Today we're going to be going over 1.4, composition of mixtures. In the last subunit, we went over compositions of pure substances, and I mentioned how the opposite of a pure substance is a mixture. So we're going to be going over that. So as always, the joke of today will be, why don't mixtures ever argue? Well, it's because they always find a solution to the problem. Alright, let's get into chemistry. So in the previous video, we talked about pure substances, and those include pure elements and an array of singular molecules, like water. But what happens when you mix water with salt? That's called a mixture, and we want to find the composition of these mixtures. And more specifically, that example of water with salt is called a solution. Every solution has a solvent and a solute. A solvent is a substance that dissolves the solute. In this case, the solvent is water and the solute is salt. A good easy way to remember this is that solvents are the solvers of the problem in which they're going to dissolve the solute. Alright, so let's use our superpower, as my old AP Chem teacher would say, and that is we get to shrink into the molecular size to visualize these atoms and molecules. So here we have 4 different scenarios. In box 1, we have a mixture, because we have 2 different substances in a container together. It's not just purely an element, and it's not just purely one molecule. We have a mixture here of element A and element B. And chemically we could write it out as A plus B. And in box 2, we do not have a mixture because it seems that all molecules are identical to each other. So going back to the idea of ratios, the ratio of each molecule is the same. So for every atom of A, there are 2 atoms of B, and the same applies for all the other molecules. So we can say that this box just has AB2. Alright, next is box 3. And this is another example of a pure substance, because if we look at the ratios again, they are identical. Every molecule is B2. They are diatomic molecules, meaning 2 of the same element. And diatomic molecules are mostly seen with gases like oxygen and hydrogen and so on. Alright, and finally box 4. As we can see, this is a mixture, because there are 2 different types of molecules with different ratios. Chemically written out, this can be AB2 plus A. Alright, so now we've visualized what a mixture is, let's get to the stoichiometric part of these compositions. Now, it's no different than finding the elemental composition of a pure substance, but this time we have to zoom out a little bit more and take a few more steps. Let me draw it out to visualize. Let's say we have a mixture, and we want to find out the composition of the pure substance in that mixture. Now, we have to derive it from the elemental composition of that pure substance. This way, we can see how pure a substance is. If we have a mixture and we want to find out the composition, we can analyze it using techniques like elemental analysis or density testing, but these are just examples, and we're not going to go into detail about them, but it's just a way to visualize it. For example, you can use elemental analysis to find the percent composition of rubbing alcohol, which is typically a mixture of alcohol and water. And the alcohol is typically ethanol or isopropyl. And by analyzing the composition, we can determine if it's 70% alcohol and 30% water, or I've seen some pretty concentrated solutions of isopropyl alcohol. Like I think one time I saw 99%. So that's really concentrated with isopropyl alcohol. And these percentages are based on the volume using molarity, but we'll go into that later. Alright, so let's look at this practice problem, and I'll walk you through it since we haven't really seen many of these. A sample of a mixture of 3 grams of potassium chloride and magnesium chloride is found to contain 0.18 grams of potassium. What percent of the sample is potassium chloride? Alright, so like I said, we need to zoom in just a little bit more. We're going to look at the mass of potassium because in the end we need to find the mass percent of potassium chloride. And since it contains potassium, we're going to use the element potassium. So the first step, as always, is to convert to moles. So let's convert 0.18 grams of potassium to moles using molar mass. So the molar mass of potassium is 39.1 grams, and we divide, and that gives us 0.0046 moles of potassium. Next, we have to find the moles of potassium chloride as a total. Now, in the previous video, I mentioned that you can use the ratios of the molecule to help you find the moles of each element and the whole molecule. And the same idea applies here. As you can tell, we have a 1-to-1 ratio of potassium to potassium chloride. So for every potassium chloride molecule, there's 1 mole of potassium. So that means that we can use the same moles of potassium for the same moles of potassium chloride. So therefore, we have 0.0046 moles of potassium chloride. Alright, so now let's convert the moles of potassium chloride to grams. I feel like I'm saying potassium chloride a lot. Alright, so we just have to multiply the moles by the molar mass of potassium chloride. And the molar mass of that is 74.55 grams. And that gives us 0.343 grams of potassium chloride. Now the final step is to divide the amount of KCl, might as well say it out loud instead of potassium chloride, by the mass of the total mixture, which is 3 grams. So if we have 0.343 grams of potassium chloride and 3 grams of the total substance, we divide it by each other, and that gives us 0.114. And since we want the percent, multiply by 100, and that gives us 11.4%. And remember sig figs, so in the original problem, we can see that we're given 2. So I'm going to round my final answer to 2 sig figs, which would just give us 11%. Alright, so here's a similar problem. I want you to pause the video and try this on your own. So here we have a 6-gram sample of a mixture magnesium carbonate and aluminum oxide, and it contains 2.4 grams of magnesium. What percent of magnesium carbonate is in the mixture? So the correct answer would be 138.8%, but since there's only 2 sig figs, it would be 140%. So let me walk you through it. The first step, like always, is to convert to moles, and we were given magnesium, so that helps us since we want to find the percent composition of magnesium carbonate. So if we convert to moles of magnesium using the molar mass, that gives us 0.0988 moles of magnesium. Now, let's use ratios again to find the moles of magnesium carbonate. Again, we have a 1-to-1 ratio. For every mole of magnesium carbonate, we have a mole of magnesium. So the moles will remain the same. So now that we know we have 0.0988 moles of magnesium carbonate, let's turn this into grams using the molar mass. So the molar mass of magnesium carbonate is 84.31 grams. And we multiply that by the mass of magnesium carbonate, and we get 8.3269 grams. And the final step is to divide by the total mass of the mixture. And that gives us 1.3888, or 138.8%. But since we have 2 sig figs, it will be 140%. Alright, let's do some more practice. I know the majority of these videos are just practice, but I assure you more practice, more practice, more practice. I will also be going over every AP Chem FRQ that I can, and I'll be breaking down each question in accordance to their unit and subunit. So look out for those videos. The practice is the best type of studying that you can do. Alright, so here we have a question. Let's read it together. The mass percent of hydrogen in pure water, H2O, is 11.2%. A chemist analyzes an impure sample of water and determines that the mass percent of hydrogen is 10.5%. Which of the following impurities could account for the lower mass percent of hydrogen in the sample? Alright, I want you to pause the video and try it on your own. Alright, welcome back. So essentially what the question is asking us is which substance would have the water be in a mixture that will have a less percent makeup of hydrogen. So let's go over each one. So option A, I like option A. Since there's no hydrogen present, it is possible that it can lower the mass percent of hydrogen in the mixture. But let's keep going. Ethanol has a high amount of hydrogen atoms in a molecule, and to be honest, my other answer choice is 2. So since we're looking for a substance that has a lower percent hydrogen concentration than water, salt is the only reasonable answer here, since there's no hydrogen, and therefore it will lower down the mass percent of hydrogen in the mixture sample. So option A is the correct one. Alright, so here we have another problem. It's more similar to the ones that we did previously before. I want you to pause the video and try it on your own. Then I'll walk through it. Alright, so the first step, as always, is mole conversion. Now, it's asking for the percent of magnesium, and we don't have the moles of magnesium present. But there's a reason why the reaction formula is given. Notice that we need 1 mole for a mole of hydrogen gas to be produced. So that means we have a 1-to-1 ratio here, meaning that the moles of H2 given, 0.05, will be the same as the moles needed for magnesium. So the moles of magnesium would be 0.05. And we can just convert that to grams using the molar mass. And that gives us 1.215 grams of magnesium. And now we just have to divide by the total mass given, which is 3 grams. And that gives us 40.5% magnesium. Alright, so now let's move to the final question. And this is in the form of an FRQ. So I want you to take those pencils out and really practice. And I recommend writing it down like you would on test day. It's super important that you feel the atmosphere and you are ready for the testing environment. Alright, so pause the video and try it on your own, and I'll come back when you are done. Alright, so we have a 0.750 gram sample of a mixture containing nickel, and it is analyzed using a reaction with hydrochloric acid, which converts all the nickel to nickel 2+. The nickel 2+ solution is then diluted to a volume of 100 milliliters and analyzed spectrophotometrically at a wavelength of 400 nanometers, with an absorbance determined to be at 0.62. The graph shown below is a calibration curve for nickel 2+ at 400 nanometers. Alright, so here we have a graph, and we haven't gone over this yet. It's photospectrophotometry, and we'll go over it in the upcoming subunits and units, but let's just break down the question part by part. So part A is asking, use the graph to determine the concentration of nickel 2+ in the solution. So using the graph, we can easily find the concentration. If we look at the problem, we can see that the absorbance is determined to be around 0.62. So if we just go to the right of 0.62 and go down to the concentration, we can see that it's around 0.0153 molarity. And it's totally okay if you didn't know that, how to do this one. It's a little tricky, and it will come soon, so don't worry about it. And M molarity here is the concentration, and it's going to be super important that we know this value for part B. So part B, well, like I said, since we have molarity, we can easily find the number of moles using the formula for finding molarity, which is M equals N over L. Now, this formula is on the new 2024 chemistry formula sheet. It wasn't when I took the exam, so you guys are really lucky ducks. So like I said, M stands for molarity, N is for the number of moles, and L is for liters. Now, we're just going to solve for N since we have the other values, so it's just simple algebra. But here's something new. Since they give us the units in milliliters, we're going to have to convert 100 milliliters that they used to dilute to liters. So we're just going to divide 100 by 1,000, and that gives us 0.1 liters. So now that we have all the values, we're just going to plug and chug. So we have 0.0153 molarity equals N over 0.1, and we're going to multiply so we can get rid of the denominator on the left, and that gives us N equals 0.00153 moles and of nickel 2+. So that's part B. And lastly, part C. So in part C, we're going to need part B. So if we have 0.00153 moles of nickel 2+, we just have to find the mass and divide by the total mass. So in order to find the mass, we just use the molar mass of nickel, and that gives us 0.0898, and divide by the total mass, which is 0.750 grams, and that gives us 0.1197, and times 100 to get percent, 11.97%. But since we have 2 sig figs in the original equation, 3 sig figs, it'll be 12.0%. Alright, so that pretty much sums it up. Subunits 1.3 and 1.4 go hand in hand and are the most calculations that you'll see in Unit 1, the most stoichiometric calculations. Just always remember to convert to moles. That will lead you, and you will always have to use the molar mass. Alright, have a good day and happy calculations.